research-focused information theory and its application in animal as well as plant breeding. And for this purpose, I would like to give a short introduction about information theory, and then I want to present some of its applications in GWAS analysis or in epistasis analysis. Before we start with the theoretical part of information theory, we should first define its first term as information. If you search this word in internet or in literature, you can find several definitions with similar meanings. Some of them I have written here for you. For example, it can be said that information is the knowledge about something or someone, or it is defined as details about the subject. It can be also said that information is the communication of knowledge or intelligence, although there are several other definitions, but as I already taught you, with similar meanings. In general, we can say that information is the knowledge about knowledge obtained from some investigation or some studies. And in information theory, it is defined as a numerical quantity indicating the indicating the number of possible outcomes or possible opportunities. Let us consider this sentence with missing letters as an example. Based on our previous knowledge, we know that in English alphabet there are 26 letters, and each of these letters could be used with certain probabilities in order to complete this sentence. And by this way, we can see that the probabilities depend on our previous knowledge, and between probabilities and the information, there is a fundamental link. Thomas Bayes showed in his study that the probabilities depend on the available information. After more than 200 years later, Shannon explained in his study that information is a function of the probabilities. Following the Shannon studies, we can say for our problem, at the beginning we have an uncertainty of 26 letters. As soon as the first letter appears, and we see that, it means we receive some information, and our information increases. At the same time, the uncertainty decreases. And step by step, we can complete this sentence and solve this problem. And here we can say that information theory is applicable to any statistical or probabilistic problem. Information theory studies with the quantification, storage of or the communication of the information. It is originally proposed by Shannon in his model of a digital communication system, and in his model there is an information source. It sends some message. Also, in our case, it is the English symbols. The message will be coded, send it to a communication channel, and after that the message will be decoded and send it to the receiver or the destination. Please keep this model in mind, and we will use it later for development of epistatic models. And in his studies, Shannon defined the quantity of the information is the entropy of the associated distributions, and it is calculated using this formula. Entropy is the measure of the average uncertainty of an outcome and has the following properties. Also, it is always non-negative. And entropy is zero if we receive no new information, if everything is clear and there is no surprise effect anymore. And entropy is maximum if all outcomes have the same probabilities. But we can extend the calculation of the entropy easily for more than one random variable. If we consider two random variables, at this time we are talking about the joint entropy, which is calculated by this formula. Or another fundamental concept is the mutual information, which we can calculate using the joint probabilities and the marginal probabilities, or which we can also calculate in terms of entropies. Easily, we can see that here in this, considering this Venn diagram, the meaning if the blue Venn diagram belongs to the entropy, or shows the entropy of the x, and the green Venn diagram shows the entropy of the y, the joint entropy is the union of the both circles, and the mutual information is the intersection area of both circles. And it means that consider X, how much information can we receive about another random variable Y. Also the calculation of the entropy and its related concepts can be also easily extended for more than 2 random variables. For example, in this case, let us consider 3 random variables. And if you look at here this Venn diagram for the circles, each of the single circles show the entropies of the single random variables, and the different unions of the circles show us the different type of joint entropies. If we take the union of all of the circles, it means it has the joint entropy of these 3 random variables. Also, the concept of the mutual information can be also extended for more than 2 random variables. In this case, all of the intersection areas show us the different concept of the mutual information. And in our studies, we are interested in the last one for the development of the epistasis model, and which is shown here. There, yellow area, gray area, cyan area. And in our epistasis model, we consider both random variables X and Y as a pair of SNP, and Z as the corresponding phenotype. In our studies, the last important concept of the information theory is the relative entropy or divergence, which is needed to quantify the differences between 2 or more probability distributions. And there are two well-established concepts of the divergence. The first one is the Kullback-Leibler divergence, which is calculated by this formula, and the second one is the Jensen-Shannon divergence, which is the improved version of the Kullback-Leibler divergence, which is calculated by this formula. So we can calculate it easily in terms of entropy. And Jensen-Shannon divergence is symmetric and bounded between 0 and 1. All of the divergence values are always between 0 and 1. Due to these properties, we prefer Jensen-Shannon divergence in our applications. In our first study, also in the first study where we are interested in the identification of important markers which are associated with low lysine concentration in fava bean. In this project, we collaborate with Professor Link and his research group, and our initial data set contains for 20 fava bean plants the genotyping by sequencing data. Using this data, we construct two groups of GWAS data. The first group contains the genotypes of plants which have low lysine concentration, and the second group contains the genotypes of plants which have high lysine concentration. And using Jensen-Shannon divergence, we compare the distribution of the SNPs in both groups. It means we compare the genotype distribution of the SNP under study in both groups and calculate the Jensen-Shannon divergence. A higher value of Jensen-Shannon divergence shows that the genotype distribution of a SNP in both groups are completely different. If the Jensen-Shannon divergence is 0, means that the genotype distribution of a SNP in both groups are completely identical. And in our group, Felix Heinrich is responsible for that. He has already applied this methodology and observed the first result. Our results show that we are able to identify novel markers whose significance were missed by classical GWAS analysis, and the importance of these markers will be tested by Professor Link and his research group. In our second applications, we are interested in the identification of epistatic interactions. In this project, we have developed a new methodology during our joint application with Professor Geiling and Dr. Müller, and this methodology is applicable to any GWAS data of plants or animals. The main concept of this methodology is the multivariate mutual information, which is calculated between the pair of SNP and the phenotype using this formula. So we can entropy of the pair of SNP plus the entropy of the phenotype minus the joint entropy. In order to develop this methodology, we adopted the idea of the Shannon's communication system, and as you can remember, in Shannon's communication system, there is an information source. In our case, the information source is a SNP. The message is the corresponding genotypes. The message will be sent, and the message will be coded and then sent to communication channel. And here we accept this communication channels as some biological processes that we cannot see that. And the output of the communication channel will be decoded and sent to the receiver as the phenotype. And the amount of the information or the association between the SNP and the phenotype can be measured using the classical mutual information between two random variables. But in epistasis model, we are interested in more than one SNP. Therefore, our input or information sources, in this case, the pair of the SNPs, and the remaining part, same, and the amount of the information between a pair of the SNP and the phenotype is calculated using this formula. And previous studies have already shown that a higher value of this multivariate mutual information metric indicates a strong association between a pair of SNPs and the phenotype. For the proof of the concept, we have analyzed a GWAS data related to bovine tuberculosis, and this data set contains more than 600,000 SNPs, and more than 600,000 SNPs for 1,151 cattle. At this point, it is important to mention that due to the high number of SNPs, there are very huge number of all possible associations. Also in our case, we have to calculate this mutual information metric more than 100 billion times. And this calculation is very challenging, therefore we need a very memory and time efficient implementation. In our group, Lars is responsible for this project, and he has already implemented the first version of this project on the CPU. His implementation takes on the CPU more than 25 hours time, and on the GPU less than 3 hours time. And applying this methodology to this data set, we first identify the associated SNP pairs, and using these SNP pairs, we construct such epistasis networks. In our network, the nodes shows nodes are related to the marker names, and the connection between these nodes show their significant associations, and the different colors show the different chromosomes of the different chromosomes. As you can see that here, there are different type of clusters in our network. There are such big clusters where several SNPs are connected with each other, and there are also such type of small clusters. A closer look at our networks shows that we are able to identify the known important SNPs as some of our hubs. Most importantly, or for us, most interestingly, we are able to identify SNPs or pair of SNPs as significant, which are strongly related to the bovine tuberculosis disease. And to summarize, we can say that information theory could be a new concept for the analysis of the different data set in animal as well as plant breeding. It can provide some complementary methods to the existing methodologies, and its application for the identification of high-order association is really easy. We can directly apply it for higher association between two SNPs or between actually more than two SNPs. And for the future, we want to improve our methodology for the next step in order to eliminate the false positive prediction. For that, our first aim is we want to identify or quantify the background level or background association level in level of SNPs and phenotype between SNP and phenotype in GWAS data, and then in the epistasis network we have seen that there are direct and indirect associations. Our next aim is the separation of the direct associations from the indirect ones. Thank you for your attention, and I'm happy about that. Yes.
Other questions, comments, please.
For the significance, we take the most easiest way. Actually, we convert the visual information value in this course and take the bigger if a visual information value has a z-score bigger than 3, we say that it's a significant one. But for me, during my PhD thesis, I have also developed a concept in order to approximate the distribution of the visual information values. We can approximate we can model the visual information values using the beta distribution, and then after that we can identify the significant ones. Actually, I took this concept from your book.